welcome to the mathematics and a new video. Today we take care of the greatest common divisor and we use a certain definition. You can read it here. In one of my last videos I showed how to derive this formula using Pick's theorem. And Pick's theorem is about calculating areas of convex polygons in the coordinate system where all the coordinates of the points are lattice points, and then there is a formula for the area using the amount of lattice points on the boundary, the amount of the lattice points in the interior, and that's how we can derive this formula. I will not repeat it here. We just take this expression as a definition for the greatest common divisor. And what we want is we want to prove some properties of the GCD, like the commutativity, then the scaling property, and some kind of invariance. And then if A divides B, we have GCD of A and B is A, and GCD of A and GCD of AB is GCD of A and B. And the interesting part of this video is, of course, using this expression. Before we start these 5 proofs, I want to introduce 2 tools which we don't prove in detail. The first one is if we have a sum from where k runs from 1 to a over the floor of b over a times k, then we can change the upper bound to b and change b and a, and so we can convert like this sum to the other or the other way around. And yeah, there are 2 summands. So a plus the sum up to a is b plus the sum up to b. This is our first tool. And the second tool is if we have this sum but the upper bound is a multiple, an integer multiple of a, then we can bring down this multiple in front of the sum plus another term. And yeah, how you can prove this? Some easy way is to use Pick's theorem and counting the lattice points. So I have a picture here. So if you consider b over a times k as a straight line, b over a times x, we get like the green line, and a over b times x, we get this orange line. And this sum is counting all the lattice points in this triangle, all of them on the hypotenuse, on the interior, on this line, except the bottom line. The same for the orange one. And now if you use Pick's theorem, you can easily show that these 2 sums are the same. Why? Yeah, this green triangle and the orange triangle, they have the same area, and so this part follows. For the second one, again we consider b over a times k as a straight line, b over a times x. We get this line, and like I said, this sum is counting all the lattice points on the triangle and in the triangle except the bottom line. And this multiple here you can check by yourself that we can count t triangles here, and we are left with some rectangles. And how much of the rectangles? Yeah, there appears the triangular numbers, and this is exactly here, t over 2 times t minus 1, and a times b is the area of the rectangle. Yeah, so check yourself, this formula makes sense. And now we can start with our first proof, and the commutativity of the greatest common divisor. Here it's not so obvious in the first sense. Yeah, we see we have here a minus b, and if we change the role we have b minus a. So in the first moment it's not so obvious, but we check it. So we start on the left hand side, GCD of AB. This is by definition a minus b minus ab plus 2 times the sum where k runs from 1 up to a b over a times k. Yeah, and now we make use of this formula. So we have this part, so we bring the a to the other side, so we have a minus b minus ab plus 2 b plus the sum where k runs from 1 to b, a over b, k minus a. Yeah, now we have minus b plus 2b is b, a minus 2a is minus a times b is b times a, plus 2 times the sum where k runs from 1 to b, a over bk. But this is exactly the definition of the GCD of b and a. So this proves our first statement. Yeah, the second one, again we start on the left hand side. So we have GCD NA and B. This is by definition n times a minus n times b minus n squared ab. Yeah, so NA and b, n squared ab plus 2 times the sum where k runs from 1 to NA over NB over NA times k. Now we make use of the second tool where n plays the role for t, and here we can cancel out an n. We have n a minus n b minus n squared ab plus 2 times. So n plays the role for t, so the t comes in front, which is the n times the sum where k runs from 1 to a, b over a times k, plus a times b times n over 2 times n minus 1. Yeah, now we can factor out 1n. And we have n times a minus b minus nab plus 2 times plus 2 times our sum, floor of b of a times k, 2 times sum plus 2 times this expression here, here the 2 they cancel out, so we have plus ab and minus 1. So we have a minus b plus 2 times the sum. This is what we want, a minus b plus 2 times the sum. This term minus ab is missing, and we get this term from here, ab times minus 1. And here we have minus nab plus nab. This part cancels out, and we are exactly left with the definition of the GCD, and this proves our second statement. For the third statement, I clean up the board and come back. Alright, so again we start on the left hand side. We have GCD a b plus ta. This is by definition a minus b plus ta minus a times b plus ta plus 2 times the sum where k runs from 1 to a of b plus ta over a times k. So here we have a minus b minus ta minus ab minus ta squared plus 2 times this sum, and I split up here the fraction, so we have 2 times b over a times k plus ta over a, which is t, plus tk. And now if we have an integer in the argument of the floor, we can bring out this integer. So we have a minus b minus ta minus ab minus ta squared plus 2 times the sum where k runs from 1 to a ba over k plus 2 times the sum, t is not depending on k, 2t, the sum where k runs from 1 to a k. And now we have a minus b minus ab plus 2 times our sum. This is by definition the GCD of ab. And we are left with minus ta squared plus 2 times this sum. Here this is the little Gaussian, and you can check that minus ta squared plus 2 times the sum, they add up to 0. I leave that for you, and so we have finished our proof for the third statement. The fourth one, if a divides b, it follows that GCD of ab is a. So if a divides b, this is by definition, there is a t. So we are just moving in the natural numbers, so there's a t in the natural numbers, that b is t times a. Alright? Yeah, and now we start again on the left hand side. So we have GCD of AB is a minus b minus ab plus 2 times 2 times our sum. Now we can plug in t times a for b. So we have a minus ta minus a times ta minus ta squared plus 2 times the sum where k runs from 1 to a. So b is t times a, so the a cancels out, so we have t times k in the floor, but t times k is an integer, so the floor of integer is of course an integer as well, in the same integer, so we can leave the floor brackets. T is not depending on k, so we have 2t times t, then the sum over k. And also here we have the little Gaussian, it's the same game like here, yeah, you see minus ta squared plus 2 times the sum, it's exactly the same here. So you've already convinced yourself that this adds up to 0. So we are left with a, and this is exactly what we wanted to prove. Alright, so we have finished our proof for the fourth statement. So the last statement, the GCD of A and the GCD of AB is the GCD of AB. So we start on the left hand side. This is by definition A minus the GCD of AB minus A times the GCD of AB plus 2 times the sum where k runs from 1 to a of GCD of AB over a times k. Now what can we do here? We use a property of the GCD. We haven't showed it here. You can try to prove this, and we make use of that the GCD of AB divides A. It divides also B, but we only need it for A. So GCD of AB divides A. This means, this is by definition, we can write A as T times the GCD of AB. Alright, so you can try to prove this one using the definition. Alright, so we plug in A T times GCD for here. So we have A minus GCD AB minus A times GCD of AB plus 2 times sum where k runs from 1 up to A, but A we write this at GCD at T times the GCD. So GCD of AB over A is 1 over T. So we have K over T. Alright? Why we do this? Now we can make use of our property here. So we have A minus GCD of AB minus A times GCD of AB plus 2 times. Here the GCD is playing the role of T. So, okay, so GCD of AB comes in front, and then we have the sum where k runs from 1 up to T of the floor of k over t. Alright. Plus a times b. So b is 1. A is t. So we have t times 1 plus t times 1 times t. The GCD is playing the role for t, so we have t times 1 times GCD of AB over 2 times GCD minus 1 times the GCD minus 1, and I write it in a short way like that. Alright, we have, you can simplify this stuff, but I want to make one note. This sum, k runs from 1 to t, so k is less than t except k equals t. If k is less than t, we have a fraction between 0 and 1. So the floor rounds down every summand to 0 except for k equals t, we get a 1. So this sum sums up to 1. So we have 2 times GCD plus, then here the 2 that cancels out. And now we make use of t times GCD is a. So here we have a, and you see minus a GCD plus a GCD, they cancel out. Minus a, this cancels with this a, and minus GCD plus 2 times GCD is exactly GCD. Okay, so pause the video and take pen and paper and try to follow all the steps. Like I said again, t times GCD, this is a, so we have plus a minus a, this cancels out, and we have minus GCD, a times GCD minus a times GCD, this cancels out, and we have minus GCD plus 2 times GCD, so we are left with GCD, and this proves our last statement. Very nice. And I wanted to prove also a mathix statement, but I haven't finished the proof yet. And this is the associativity of the GCD. So if we have GCD of A and the GCD of BC, then this is the same as the GCD of A, B and C. This is what I want to prove also, but I haven't finished the proof yet. There must be somewhere a trick which I don't know, or some crazy manipulation for floor sums. If I finish the proof, I will make also a video about it. Try this. If you can manage this, let me know, write an email, I appreciate it. So I hope you liked the video. See you next time. Have fun with this. And
I welcome
bye-bye.
constructive criticism. If you have any suggestions or video requests ready, feel free to write me an email, suggestion@easymathematics.de. And if you still feel like doing math, further suggestions are now displayed. So have a great time. See you next time.